Chapter 22, Gauss's Law. In this chapter, we cover these topics: electric flux, Gauss's law, applications of Gauss's law, experimental basis of Gauss's law, and Coulomb's law. Section 1. Electric flux through an area is proportional to the total number of field lines crossing the area. Here in the left, we will see three different depictions of this situation where we have a uniform electric field shown with the red lines in parallel from left to right, indication that the field is from left to right, the electric field. And we have a green area indicating of the surface through which we want to see the flux of the electric field. We have to consider either in part B of the component of the electric field normal to this area, or alternatively, we can consider in situation C the normal cross-section of the area perpendicular to the field lines. Therefore, the electric flux, as indication by phi, which is the Greek letter capital Phi, E, which is electric flux, is a multiplication of the normal component of the field multiplied by the area, E normal multiplied by A, capital A, area, or the electric field multiplied by A normal, which is the normal component of the field surface with respect to the electric field. And this can be written as E times A times cosine of theta, which is the angle theta between the perpendicular to the area and to the uniform electric field. We can write this as a dot product between two vectors of E, electric field, and A, the surface, E dot A, which is a vector multiplication of vector E and vector A. The angle between them is theta, so the result would be a scalar, a number. So we will have magnitude of E, magnitude of A, and the cosine of the angle between them, which is theta here in our case. Moreover, we can consider the flux through a closed surface. In this scenario, if we consider small pieces of field, if we have smaller pieces on smaller surfaces, we should consider E sub I dotted with the pieces of surface delta A, and we should sum over all different segments and patches of the surface from number 1 to number n, and this gives us the total flux phi sub E. Alternatively, we can take the integral if the sizes of the delta A is infinitesimally small as a derivative or differentiation of the surface dA, and we can have the closed integral, the integral over the closed area of E dot dA. Okay, now let's take a look at problem number 2 from the book as an example. The Earth possesses an electric field of average magnitude 150 Newton per Coulomb near its surface. The field points radially inward. Calculate the net electric flux outward through the spherical surface surrounding and just beyond the Earth's surface. To solve this problem, we have to use the equation for the flux, electric flux that I just mentioned, E dot A, the flux of the Earth. The electric flux of the Earth is the electric field dotted with A, the vector normal to the surface. But imagine that this is the Earth. We have a capital A vector, normal to the surface, moving outward from the Earth's surface. And on the other hand, we have the electric field, which is directing radially inward. The angle between these two vectors, theta, is equal to 100 degrees. Okay, so let's plug in the numbers. So we have E dot A, these are vectors, which means that we have multiplication of the magnitude of the electric field times the magnitude of the surface times the cosine of the angle between these two, which is 180 degrees. And this is equal to 150 Newton per Coulomb multiplied by 4 pi r squared, this is the radius of Earth, squared, times cosine of 180 degrees, which is equal to -1. The radius of Earth is 6.38 times 10 to the 6 meter. And if you plug in all these numbers together, the flux of the electric field toward the surface of the Earth is minus 7.7 times 10 to the power 16 Newton meter squared per Coulomb. Another example, problem number 4 from the book. A uniform field E is parallel to the axis of a hollow hemisphere of radius r, as shown in this figure down in this slide. Part A asks, what is the electric flux through the hemispherical surface, which is shown in the grayish hemispherical area? And B asks, what is the result if E is instead vertical, perpendicular to the axis, and is still uniform? Okay, so for part A, we should note that the electric field that is shown here is actually directed from left to right toward the surface of the hemisphere here. We will see we have a cross-section indicating that the line of the field are entering the hollow hemisphere, and we have these lines of the field getting out on the surface. So the same lines are entering from the circle that I just put lines on it, and the same lines will exit on the right side of the hemisphere. So in order to calculate the flux, we can use the same equation as the integral of E dot dA, but you should pay attention that we don't need to take the integral over the whole surface of this hemisphere, but rather we can calculate the surface of this circle here as the cross-section of the area that the fields are entering and are normal to those. But we have to pay attention that the vector for the electric field is rightward, while the vector to the surface of the circle is actually leftward. So the cosine of the angle between these two is -1, because the angle between these two vectors is 180 degrees. So we say EA cosine of 180 degrees, and that gives us minus E, and for the surface we say pi r squared. But this circle is not what we're intended to. We are talking about the hemisphere on the right. This is the flux into the hemisphere, but the question of this problem is asking for the electric flux which is passing through this one, so that I have shown with the green arrow on the right. So we have to multiply this with a minus sign, and this gives us pi r squared times E. For part B, it asks, what if the electric field is vertical to the axis of the surface? So the scenario would be, this is the hollow hemisphere, but the electric field lines are still uniform, but vertical. And this is going to be the axis of the hemisphere. So vector A, or the vector A here. So for this scenario, we have to pay attention that if we have some flux coming into this surface, the same flux is getting out from the opposite direction. So we can write down the total flux is equal to the flux in minus the flux out, and we know we have the same flux coming in and the same flux coming out, the flux in is equal to the flux out because of the symmetry of the problem, and the total flux is 0. Section 2. Gauss's law. The net number of filled lines through the surface is proportional to the charge enclosed and also to the flux, giving Gauss's law as the integral over the closed surface of E dot dA is equal to the charge Q enclosed over epsilon naught. This can be used to find the electric field in situations with a high degree of symmetry. For example, for a point charge, we can take the integral over the surface enclosing the charge Q as indicated with the green sphere, which is enclosing the charge Q on the right here, and take the integral over the closed surface of E dot d. The electric field is uniform all across the surface of the sphere, and the area of the sphere is 4 pi r squared. R is the radius of the sphere, and the flux is 4 pi r squared multiplied by E, and that is equal to the enclosed charge Q divided by epsilon naught. And from here we can calculate the electric field by solving this equation for electric field to get the result that we were expecting from the Coulomb's law. The electric field is equal to 1 over 4 pi epsilon naught multiplied by Q divided by R squared. On the other hand, we can approach this problem by using Coulomb's law to evaluate the integral of the field of a point charge over the surface of a sphere surrounding the charge to give us the integral over the closed surface of E dot dA, and the electric field is 1 over 4 pi epsilon naught Q divided by R squared times dA. Everything is constant here, and the integral over dA is 4 pi R squared. If you multiply them together, we will get the Q divided by epsilon naught, which is the Gauss's law. Looking at the arbitrarily shape of the surface A, and here we are showing A1 or A2. A1 is a symmetric sphere, but A2 is an arbitrarily shaped surface. We see that the same flux passes through either of the surfaces. Therefore, this result should be valid for any closed surface, and that's the power of the Gauss's law. Finally, if a Gaussian surface encloses several point charges, the superposition principle shows that the integral over the closed surface of E dot dA equals to the integral over the closed surface of the sum over all the electric fields enclosed dotted with dA, and that is equal to the sum over all the enclosed charges Qi divided by epsilon naught, and that is equal to the total net charge enclosed in the closed surface divided by epsilon naught. Therefore, Gauss's law is valid for any charge distribution. Note, however, that it only refers to the field due to charges within the Gaussian surface. Charges outside of the surface will also create fields. To illustrate this point further, let's look at problem number 6 in the book as an example. The figure below shows 5 enclosed surfaces that surround various charges in a plane, as indicated by S1 through S5. Determine the electric flux through each surfaces. The surfaces are flat pillbox surfaces that extend only slightly above and below the plane in which the charges lie. So you don't need to worry about the three-dimensional calculations. Okay? So the net flux, according to the Gauss's law, the net flux through each enclosed surface is determined by the integral over the closed surface of E dot dA. And that is equal, according to the Gauss's law again, to the charge enclosed over epsilon naught. And the Q enclosed is the net charge inside that particular surface. So for surface 1, we have flux 1 is equal to, surface 1 is here, the total net charge is plus Q minus 3Q, and that gives us minus 2Q over epsilon naught. So phi 1, or the flux for surface 1, is minus 2Q over epsilon naught. For the second surface, S2, is enclosing the plus Q, the plus 2Q, and minus 3Q. So the total net charge inside the surface S2 is 0. So phi 2 is plus Q plus 2Q minus 3Q divided by epsilon naught. Total of the charges are 0, so the total flux is 0. For surface 3, the third flux is the net charge of plus 2Q and minus 3Q. So we have plus 2Q minus 3Q divided by epsilon naught, and that gives us minus Q divided by epsilon naught. For surface 4, flux is the enclosed charge, which is 0. There is no charge enclosed, therefore there is no flux. So the net flux through this area, S4, is 0. For the fifth surface, phi 5 is equal to the total charges enclosed, which is 2Q divided by epsilon naught. Okay, now let's look at problem number 10 from the book as another example. A point charge Q is placed at the center of a cube of side L. What is the flux through one face of the cube? So if we have a cube, which is something like this, and we have a charge Q enclosed in that cube, cube has 6 surfaces. So this is one surface, this is another surface, this other one here, and we have 2 surfaces on this side and in the back of the cube. So we have a total of 6 surfaces of forming this cube. So the flux of each face is 1/6 the flux total, okay? And the flux total is the integral over the enclosed surface, and that gives us the enclosed charge divided by epsilon naught. So we will have Q enclosed charge divided by epsilon naught. So the total flux from one face is 1/6 of the total flux from the cube. Okay, section 3, applications of Gauss's law. The difference between the electric field outside a conducting plane of charge and outside a non-conducting plane of charge can be thought of in 2 ways. The first method is by thinking the field inside a conductor is 0, so the flux is all through one end of the cylinder. And the second way of thinking is the non-conducting plane has a total charge density sigma, whereas the conducting plane has a charge density sigma on each side, effectively giving it twice the charge density. Therefore, the procedure for Gauss's law problem includes these steps. The first one is to identify the symmetry and choose a Gaussian surface that takes advantage of it with surfaces along surfaces of constant field. 2, by drawing the surface. Third, by using the symmetry to find the direction of the electric field. 4. To evaluate the flux by integrating. The 5th step is to calculate the enclosed charge. And finally, the 6th step is to solve for the field. Alright, now let's look at problem number 20 from the book as an example. A flat square sheet of thin aluminum foil, 25 centimeter on the side, carries a uniformly distributed 245 nanocoulomb charge. What approximately is the electric field? A, 1 centimeter above the center of the sheet, and B, 15 above the center of the sheet. So since this problem is asking for the approximate electric field, when we are close to the sheet, we can approximate this as an infinite sheet. And we can use the result of example 22.7, and we can assume that the charge is enclosed over both surfaces of aluminum. So we can write the electric field is the density of charge over 2 epsilon naught. The density of the charges as 245 times 10 to the minus 9 coulomb divided by the area of the aluminum foil, which is 25 times 10 to the minus 2 meter squared, divided by 2 times 8.85 times 10 to the minus 12 Coulomb squared divided by Newton times meter squared, and that gives us 2.2 times 10 to the power 5 Newton per Coulomb away from the sheet. Okay, so if this is the sheet, this is the charge, and this is very close, 1 centimeter above the center of the sheet, and the field, the charge of the sheet is positive, so the field is upward. For part B, this was part A. For part B, when we are farther away from the surface and we are 15 above the surface at this point, we can approximate it as a point charge. So we can imagine that the whole sheet of aluminum with all the charges is considered as a point charge. So we have a point charge Q here, and we're going to calculate the electric field at this point. Again, the point charge is positive on this sheet of aluminum, therefore the electric field is still pointing upward. That's a direction. But how about the magnitude? We can say electric field is 1 over 4 pi epsilon naught. This is from the Coulomb's law. The charge Q divided by R squared. And R is the distance from the point we're calculating to the aluminum foil that we're considering. It's long enough, large enough, and we can imagine the whole charge of the aluminum foil sheet is dense in the center as a point charge. So that is equal to 8.988 times 10 to the power 9 Newton meter squared divided by Coulomb squared, multiplied by the charge of 245 times 10 to the power minus 9 Coulomb divided by 15 meter squared. The electric field in this scenario would be 9.8 Newton per Coulomb away from the sheet. Okay, another example, problem number 26 from the textbook. The electric field between two parallel square metal plates is 130 Newton per Coulomb. So we have two square plates in parallel, and the size of the plates is 65 centimeter, and they are separated from each other by 3 centimeter. What is the charge on each plate? Alright, to solve this problem, we note that 3 centimeter is much smaller than 65 centimeter, and we can imagine that the size of the plates is infinite in size compared to the separation between the two plates. And also we are going to ignore the edge effects. Therefore, we can use the results of problem 24a, and that is electric field is equal to sigma, the density of charges on each surface, divided by epsilon naught. The density of charge is defined as charge Q divided by the surface A over epsilon naught, and we can solve this for Q, charge Q. Q is equal to epsilon naught E times A, which is the surface. The electric field is 130 Newton per Coulomb. The epsilon naught is 8.85 times 10 to the power minus 12 Coulomb squared divided by Newton meter squared, and the surface is 65 centimeter or 0.65 meter squared. If we do the calculation, charge Q will be 4.9 times 10 to the power minus 10 Coulomb. Section 4. Experimental basis of Gauss's and Coulomb's law. On the right, you're looking at an experiment which is shown that we have a container which is a conductor and is isolated with an insulator from the Earth or from the universe. We enter a ball containing some charge into this container, and as we touch it, in section B, as we touch it and have it in contact with the conductor, the charges will be transferred to the conductor and they will be accumulated outside of the conductor. In part C, when we take the ball out, all of the charges are transferred onto the conductor, but they are sitting outside of the container conductor. In this experiment, Gauss's law predicts that the charge on the ball flows onto the surface of the cylinder when they are in contact. This can be tested by measuring the charge on the ball after it is removed, and it will be seen that it will be zero because all the charges are depleted to the cylinder. Summary of chapter 22. The electric flux is given by phi sub e equals to the integral of E dot dA. The Gauss's law says the integral on the closed surface of E dot dA is equal to the enclosed charge Q divided by epsilon naught. Gauss's law can be used to calculate the field in situations with a high degree of symmetry. Gauss's law applies in all situations and therefore is more general than Coulomb's law.